All right, so let's talk about this week's lab. So here we're going to be doing electrostatics, so something that we're going to be actually talking about starting Monday, which is actually when you do this lab, but that's okay. We'll see what we actually get. So first thing to talk about is actually what's known as the electric force. So the electric force is a force which is between two objects which have charge. So we'll talk about what charge is, but everybody should be somewhat familiar with charge from things like chemistry. But in general, we have three different types of charges. We have a positive charge, we have zero charge, and we have a negative charge. So it turns out that the electric force is an attractive force as long as I have two objects which are oppositely charged, meaning I can have one positive charge, one negative charge, or one negative charge, one positive charge. So this will then result itself in an attractive force. However, if they have the same charge, meaning if there were two positive charges or two negative charges, these two things are actually going to repel from each other. So it's actually a little bit more complicated than gravity, because gravity is always an attractive force because it has one sign of charge in that case, which is the mass. Right? So that's the fundamental quantity in here. But the electric force is a little more complicated. So now, as long as it has a charge, then it's going to feel a force, but that force is now dependent on how those two charges actually relate to each other. So the force, which is actually known as the Coulomb Force, says that the force between the two charged particles goes as K. So this is another K value that we're going to have to pay attention to. This is not the wave number and is not the spring constant. It is a new K value, but we'll talk about that when we get there. Is equal times the absolute value of the charge Q1 times the absolute value of the charge Q2 divided by R squared, where R squared is, or at least R, is the center to center distance between the two objects. Now, technically, this is only true for point charges, but this is what we're going to work with for now. So, okay, so here, if I have like charges, the direction of the force then is going to be repulsive. So these guys are going to repel away from each other. And if I have like charges, then these things are going to be attracted to each other. Now, from here, we're going to define something else, which is what's known as the electric field. So electric field is always denoted by a capital E with an arrow over top of it. Unless we're dealing with a magnitude, then it's just a capital E. So not to be confused with energy. So this is what we call an electric field. So it turns out that the electric field is a disturbance which permeates through all of space, which is the result of an object having charge. We'll talk about why this actually is in class, but basically what this thing says is that as long as an object has charge, it sends off this field, which we'll talk about field as well, but it's something which permeates through all space as a result of some charge here. Now, it turns out that the electric field originates on a positive charge and then terminates on a negative charge. So meaning if I drew what are called the electric field lines, which is just a visual representation of what the electric field looks like, if I have a positive charge, then my electric field lines have to point radially away from the positive charge. Or if I have a negative charge, it has to point radially inward to that negative charge. We'll talk about how to actually add these things together in the lab, or at least in lecture. And the last component of this lab, you can see this when I turn it this way, is what's known as a conductor. So a conductor is a material where the charges are allowed to move freely inside of that material. Let's see if I can move this so you can actually see what I'm talking about. There we go. A little better. So good. So this is a conductor. So a conductor is a material where charges are allowed to move freely within inside of it, which means that this is basically a metal. So metals allow for charges to move freely through. So what does that mean? So that means if I had an object here, this is my before picture, where this thing has zero net charge to it. So my total charge here, Q total, is equal to zero, because I have three positive charges and I have three negative charges, so the total amount of charge is equal to zero. Now, if I brought in a charged object, here let's say I had a rod, which has a charge of negative, so this has some negative charge, so this is Q equal to some negative number. What happens in this case then is the charges inside of the conductor are allowed to move freely within inside of that conductor, which basically means that what we learned over here is that when I bring this charged rod near then this conductor, the positive charges then will move closer to the rod because they're attracted to the rod, Simultaneously, all the negative charges will actually move to the opposite side because they are going to be repulsed by this rod. So ultimately, what this should do then is create a net force then between the rod and the object. So what you're doing in lab then is putting all these things together. So we're going to be playing with our pitfalls. So what's a pitfall? So what a pitfall is, just a second, I'll knock over too many things. Carry it this way. So this is our experimental setup. So this is basically the same thing that we use for the harmonic oscillation. Sorry, I'm using my iPad today because I forgot to bring the other laptop, the one I brought with me today. The audio actually doesn't work in it. So I'd be sitting here talking away and you wouldn't actually be able to hear it. So anyways, here's the pitfall. So here we have, again, a ring stand. We have the same apparatus that we had up here. We're then going to hang a piece of string, and then this is just aluminum foil. So here I'm going to crumple up the aluminum foil so that it creates a small ball, okay? Now, this thing is uncharged, which means it has zero net charge to it. So what we're going to do in this lab is we're going to take this guy. So this is just a PVC piece of pipe. And we're going to take this, which is then simply a piece of wool, and we're going to go ahead and rub away. So what you want to do in this case is rub this guy. So what we're doing here is we're doing what's called static electricity, where here what we're doing is we're stripping off electrons from the wool here, putting them then onto the PVC rod, causing the rod then to end up with a negative charge. So here, this is what's called conservation of charge. I'm pulling off the charges from here, putting them onto here so that the total net charge is simply equal to the same. So as I rub this thing off, more and more charges I put on here. Now, all we're going to do is bring this guy near him. And what we should see here is we can actually create an attractive force. So what you're going to be doing in this lab is basically playing with exactly this. So you're going to be taking the PVC rod, taking the wool here, rub it to put charges on here, and you'll be doing different things then with the pitfall here. So again, it's just a piece of string, aluminum foil crumpled up on here. So this is my conductor. And then what you want to do is, as the lab manual says, basically just draw pictures. Okay? So we're going to use these ideas of electric force, electric fields, and the fact that this is a conductor where the charges are allowed to move freely, to then describe why was this pitfall attracted to this rod. So this is part one. So in part one, we're going to do different things. This is the first part we're going to do. Another thing we're going to do is we're going to go ahead. I've already stripped off all the electrons, which is why we don't really get much of it. You still get some sort of attraction. But here, then you want to go ahead and touch the metal, right? Touch the pitfall, touch the aluminum foil, and watch what happens. Right? So then what we're doing in this lab then is basically describing what is happening in words and then drawing pictures to try to figure out why this is actually happening. Okay? So this lab, even though it says lab report, it's not a full lab report because it's actually just descriptions with pictures and trying to understand what's actually happening here. So here it's not a full formal lab report, so we don't actually need to type everything out and write all that out. So here you're just going to be answering the questions on what it's asking you to do. So it says do this, what did you observe, and now try to understand what's happening by drawing pictures. So that's the first part of the lab. Second part of the lab is you're simply going to add another pitfall. That's it. So here you're going to take another piece of string, take another piece of aluminum foil, create a second pitfall, and then you want to basically do all the same things, but now with the two pitfalls, again, drawing pictures, answering the questions on what it is that you see, what do you observe, write all that out, and then, again, draw pictures to try to understand what is going on based off of what we know about forces, conductors, and electric fields. Okay? So, again, it's not a full lab report. There's also no calculations in this lab, so you're not actually calculating anything. So the only thing you're doing is actually just describing what you're actually seeing, and then going ahead and drawing pictures to try to understand what's actually happening here. Okay. So again, electric force is force between two objects which are charged. Even though this thing is not charged, but we still end up getting a force because of the fact that the charges are allowed to move freely within inside of the material. Okay. This is what's known as induction. Okay. When I actually touch this to here, I get a different effect, which I won't ruin for when you actually do the lab, but that's actually what's known as conduction because it has direct contact between the two. So there what you're doing is you're transferring charge from the rod to the object and then seeing what happens in this case. So okay, no calculations in this lab, even though it says report. It's basically just writing out all of your observations, drawing pretty pictures. If you want, you can also take pictures of the actual experimental apparatus, showing what you're actually doing. It's a nice thing that you can put in there. But again, it's not a formal lab report. It's just writing out all your observations, putting in pictures to demonstrate what it is that you're, to understand why it is that it's doing what it's doing. And then it's just submission of that. So that's it. So good luck. Ask questions during lab. See you later.